Hello, this is the 11th video on my multivariable calculus course. In this video, we're going to first start talking about quadratic surfaces and then limit and continuity. So first, a few examples on quadratic surfaces. And we did a few examples in the previous lecture. Sketch and name each of the following surfaces. Okay, so if you look at the first one, this looks like a sphere. If we didn't have the 4 or 9, we would have a sphere. So what's the difference between this and a sphere? Well, if you plug in x equals 0, you're going to end up getting y squared over 4 plus 9z squared equals 1, which is an ellipse on the yz plane. Similar to that, we can plug in y equals 0, we get another ellipse on the xz plane again, and same for the z equals 0. So we have a shape that is ellipse on all three different directions. So if we put the information here together, we're going to end up getting this shape. So let's draw the XYZ axis. We have an ellipse in this direction. We have another ellipse in the other direction. And we have an ellipse in this direction. So putting these together, it's sort of like a sphere, but it has been stretched in different direction. And this is called an ellipsoid. So the name of this shape is an ellipsoid. We can also find its intercepts. So the x-intercept would be when y and z are both 0. So that gives us plus or minus 1. So the points that intersects the x-axis are going to be plus 1 and minus 1 on the two sides of the x-axis. If we look at the y-intercept, so y-intercepts are going to be when x and z are 0, we would get plus or minus 2. So the intersections here and here are going to be plus 2 and minus 2. And if we look at the z-intercepts, we would have to set x and y equals 0, and z becomes plus or minus 1/3. So the bottom and top are going to be 1/3 and negative 1/3. So this is called an ellipsoid. Okay, let's look at the next one. X squared plus 4y squared equals 1. If we look at this graph on the xy plane, we know what this shape is. This is an ellipse on the xy plane. So because there is no z component here, there's no z involved in this equation, we will take the equation on the xy plane, the shape on the xy plane, and then we move it up and down. So on the xy plane, we have an ellipse, and then we take this ellipse, and then we can basically like move it up and down. So what shape is this? This is going to be a cylinder, but it is an elliptic cylinder because the cross sections are ellipses. So it's an elliptic cylinder. All of the cross sections parallel to the xy plane are ellipses. Okay, let's look at the next one. The next one is z plus 9x squared plus y squared equals 1. Let's find z from here. This is 1 minus 9x squared plus y squared. So last time we saw that z equals 9x squared plus y squared. It is a paraboloid. It is in fact an elliptic paraboloid. So let's graph that one first. So z equals 9x squared plus y squared would look like this. It would be a three-dimensional version of a parabola, so it's a paraboloid. Now if I negate this, I would be flipping this about the xy plane. So this would be negative of what I have over there, which is z equals negative 9x squared plus y squared. And if I do 1 plus that, it means I'm moving it 1 unit up. So the final answer is going to be this shape. So this is x-axis, y-axis, and z-axis. It would be a shape, it would be a paraboloid, but the vertex is not the origin. The vertex is z equals 1. 0, 0, 1 is the vertex. So this is an elliptic paraboloid, or simply a paraboloid. Okay, finally the last one is z equals y squared. Let's graph that one. So what is z equals y squared? So notice that there is no x involved. So if I draw this shape on the yz plane, then I can move it along the x-axis. Well, on the yz plane, I have a parabola. So this is the parabola on the yz plane. And I'm moving this parabola along the x-axis. So what would I get? I would get this parabola along the y-axis, along the x-axis. So I would get a shape like this. And this shape is called a sheet. And it is called a parabolic sheet, or simply a sheet. So anytime you have a graph and you're moving it along another, and it's missing one of the variables, you're taking that graph on the xy plane or yz plane or xz plane, and you're moving it along the missing axis. Okay, so let's now talk about limits and continuity. So we have talked about limits of functions of one variables in single variable calculus. Here we're going to talk about limits of functions of two or three variables. And for the most part, we will focus on functions of two variables. So limits of this form or this form, x, y, z approaches some given point x naught, y naught, z naught, and the function is a function of three variables. So these are the two types of limits that we're going to talk about. Okay, so what is the limit of a function? Limit of a function is this. It means if xy is close to x naught, y naught, then f of xy is close to the limit. Let's say the limit is L. So this is what it means. And this is this is not an official definition. It's not a mathematical definition, but it's like roughly speaking, this is what it means. Now, what does it mean that xy is close to x naught, y naught? It means if we plot these points on the xy plane, the distance between these two is small. So in other words, we could say if the distance between these square root of x minus x naught squared plus y minus y naught squared is small, then f of xy minus L, the distance between these two, is also small. So this is again unofficial definition of limit. So the distance between these two points is what matters. Now if you approach x naught comma y naught in the two-dimensional space, you can approach it from any direction. So if this is your x naught comma y naught, you can approach it from any direction, from any line through that point, or from, let's say, a parabola through this point, you can approach the point x naught comma y naught. So the point is, limits in two dimension, functions of two variables or three variables, are going to be much more complicated than functions of one variable. So in functions of one variable, if you're approaching x naught, you could either approach it from the right or from the left. There's only two possibilities. But in two dimension, you can approach from any direction, any line through the point, or any parabola, or any function that goes through that point. Okay, to see how we can evaluate limits, let's do a few examples. And that's basically what we're going to do for the rest of this lecture. We're going to talk about some examples on limits and then continuity. Evaluate each of the limits below or show they do not exist. So the first one is limit of sine of x squared plus y over x squared minus y squared. Okay, so x and y approach 1 and pi, which means x approaches 1 and y approaches pi. Let's simply plug in the values and see what we get. So we get 1 squared minus pi squared. So this would be sine of 1 plus pi divided by 1 minus pi squared. And there's no ambiguity here, so that would be our answer. Okay, so let's look at the next one. For the next one, if we plug in 0, 0, we get 0 squared over 0 squared plus 0 squared, which is an indeterminate form. Now we do not have L'Hopital's rule for functions of two variables. So L'Hopital's rule does not apply. So what do we do instead of L'Hopital's rule? Here are the steps that we're going to have to take. Let me put it on a diagram. So this is the origin, this is the point we are approaching. And the first thing we're going to do is we're going to approach this point along different lines through the origin. So let's say we are going to approach the origin along the line y equals x. Let's see what we get. Y squared over x squared plus y squared becomes x squared over x squared plus x squared, which is 1/2. So if I approach the origin along y equals x, I will get 1/2. So the limit is 1/2 along that line. Now what about if I approach the origin along the line y equals 2x? Let's plug it in to see what we get. Y squared over x squared plus y squared becomes 4x squared over x squared plus 4x squared. Simplifying this, we get 4 over 5. Now, along y equals x, we get 1/2. Along y equals 2x, we get a different number. So what does that mean? Well, we got two different values. That means the limit does not exist. Okay, so let's look at one more example. This one is y cubed over x squared plus y squared. So how do we deal with this one? Let's try the same thing. So the function was y cubed over x squared plus y squared. Let's plug in different lines and then see what we get. So if y equals x, we get x cubed over x squared plus x squared, which is x cubed over 2x squared, which is x over 2. Now xy approaches the origin, which means this approaches 0. Let's try something else. Y equals 2x. That would give us 8x cubed over x squared plus 4x squared, and that would be 8x over 5, and that also approaches 0. So I got the same number along these two lines, but that doesn't tell me anything. So it doesn't tell me that the limit exists. It just tells me that along these two lines we got the same number. Now, is there a possibility that there is another line that gives us a different number? Well, it's possible. So how do I rule out all of the lines? Well, if you look at the xy plane and look at the origin, what are the lines that go through the origin? Well, they're either of the form y equals mx, or they are the line x equals 0. There's only two possibilities for lines through the origin. So let's try all of these lines. So let's see if we can get something that is in terms of the slope, which means the limit would not exist. So let's plug in y equals mx. We would get m cubed x cubed over x squared plus m squared x squared. Let's divide off by x squared. We get m cubed x over 1 plus m squared. As x approaches 0, this approaches 0. So all of the lines through the origin gave us 0, except for the y-axis that we haven't tried yet. So let's try x equals 0. X equals 0 gives us y cubed over 0 squared plus y squared, which is y. That also goes to 0. Now, what does this tell us? It does not tell us that the limit is 0. Let me actually write this down, because this is a very common error. This does not tell us that the limit is 0. What it does tell us is if there is a limit, then the limit would be 0. So that's really all it tells us. Okay, now we suspect, so let me actually write this down. We suspect the limit might be 0. Again, it doesn't tell us the limit is 0. It tells us that it might be 0. Okay, so let's now prove that in fact the limit is 0. So in order to solve the problem, we will use squeeze theorem. So let me go over this one. And there's two methods for using squeeze theorem for this particular problem. So if you look at the function y cubed over x squared plus y squared, well, I know that x comma y approaches the origin. So what does it mean? It means the distance between the origin and x comma y is getting smaller and smaller. So the distance between these two is r in polar coordinates. And given that at the bottom I have x squared plus y squared, which in polar coordinates it can be simplified, I'm going to use polar coordinates. So I will give you two different methods for this one. So method number one is polar coordinates. Okay, so let's plug in x equals r cosine, y equals r sine. Numerator becomes r cubed, sine cubed, and denominator x squared plus y squared is r squared. So this is going to be r sine cubed of theta. Now I would like to use the squeeze theorem. I know that r approaches 0, but this one, the limit of this one does not exist. Why? Because if xy approaches the origin, then point could be anywhere in the first, second, third, or fourth quadrant. So angle theta, if this is the x-axis, this angle theta could be really anything between 0 and 2 pi. But what we know is that this quantity is between quantity sine cubed is between 1 and -1. So in other words, and since I'm going to use inequalities, I'm going to put an absolute value in there. In other words, r sine cubed of theta is going to be less than or equal to sine cubed is less than or equal to 1. In absolute value, it's still less than or equal to 1. So that's less than or equal to r, which means r sine cubed of theta is between -r and r. So bottom line is this. Bottom line is y cubed over x squared plus y squared is between r and -r. But now, the limit as r approaches 0 of r and -r, they are both 0. Since xy approaches the origin, r approaches 0. So the limit of this side and this side are both 0. So by the squeeze theorem, in fact, the limit must be 0. So by the squeeze theorem, limit of y cubed over x squared plus y squared is in fact 0 as xy approaches the origin. Okay, so that was method number one. I will do one more, give you one more solution for this problem. So here's method number two. We are going to use inequalities to get rid of the denominator. So if you look at y cubed over x squared plus y squared, I still need to put absolute value because I'm trying to use inequalities. And when you're dealing with inequalities, you have to be careful about things being negative or positive. So if you multiply both sides of an inequality by a negative number, then you'll have to flip the direction. So it's better to just start with absolute value and then open up the absolute value. We can write this down as y squared over x squared plus y squared times absolute value of y. I broke down the numerator as y squared times y. Now, look at this fraction. In this fraction, the numerator and denominator are both positive, or at least non-negative. Numerator is less than the denominator, which means this fraction does not exceed 1. So this is less than or equal to absolute value of y, which means I can say y cubed over x squared plus y squared is less than or equal to absolute value of y and greater than or equal to negative absolute value of y. Now, since xy approaches the origin, limit of absolute value of y and negative absolute value of y, they are both 0 as y approaches 0. Because xy approaches the origin, y approaches 0. So by the squeeze theorem, so very similar argument again here. By the squeeze theorem, limit is in fact 0. Limit of y cubed over x squared plus y squared is in fact 0 as xy approaches the origin. So notice that the bottom line in this solution was the same. The only difference was in the inequalities that we used. But the bottom line of both of them was using the squeeze theorem. Okay, so let's do one more example. And I'll go over this one completely again. So find the value of constant c for which the following function is continuous at the origin. So before I can do this problem, let's talk about continuity. So what does it mean for a function to be continuous? The definition is the same definition that you have seen in single variable calculus. So f of xy is continuous at a point x naught y naught if the limit of f of xy is the same as f of x naught comma y naught as xy approaches x naught comma y naught. So this is when we say it is continuous. And same thing for functions of three variables. So f of x, y, z is continuous at x naught comma y naught comma z naught. So the exact same definition. If the limit as x, y, z approaches x naught, y naught, z naught of f of x, y, z is equal to the value of the function at that point. So this is the same definition that we had in single variable calculus. Okay, so given that we're going to solve this problem. Find the value of constant c for which this function is continuous at the origin. So what do we need? We need the limit of f of xy as xy approaches the origin to be exactly f of 0, 0. But what is f of 0, 0? Well, it is exactly c, because f of 0, 0 is obtained from the bottom one. F of anything else is obtained from the top one. So what we want to do is we want to find the limit of f of xy as xy approaches the origin. So let's look at x to the fifth over x to the fourth plus y to the fourth. And we're going to have to find the limit of that. We can approach along different lines again to see what the limit is. So y equals mx gives us x to the fifth over x to the fourth plus m to the fourth x to the fourth. Simplifying, we get x over 1 plus m to the fourth, which gives us 0. So we suspect that the limit is in fact 0. So we're going to take x to the fifth over x to the fourth plus y to the fourth. And we are going to separate this into x to the fourth over x to the fourth plus y to the fourth. So I'll have to show that this is less than something that goes to 0 and then apply squeeze theorem times absolute value of x. Now again, this fraction does not exceed 1. So this gives us less than or equal to absolute value of x, which means x to the fifth over x to the fourth plus y to the fourth is less than or equal to absolute value of x, greater than or equal to negative absolute value of x. So now the limit of absolute value of x as x approaches 0 and limit of negative absolute value of x as x approaches 0, they are both 0. So by the squeeze theorem, the limit of the middle is also 0. Limit of x to the fifth over x to the fourth plus y to the fourth as xy approaches the origin is also 0. Now, notice that in this case, because the denominator is x to the fourth plus y to the fourth, use of polar coordinates is not going to be very helpful. It is possible to do this problem with polar coordinates, but it's going to be significantly more complicated. So I'm going to move on to one more example. Okay, evaluate this limit or show it does not exist. So we're going to do the same thing again. So we're going to approach the origin along the line y equals mx. So let's see what we get. We get m to the fourth x to the fourth over x squared plus m to the fourth x to the fourth. Let's simplify this, although this would be x squared. So both numerator and denominator factor x squared, so we can cancel. We get 1 plus m to the fourth x squared. As x goes to 0, this goes to 0 over 1, which is 0. So you might think, okay, maybe the limit is in fact 0, but we haven't tried the y-axis. So let's try that. The y-axis is x equals 0. That gives us y to the fourth over 0 plus y to the fourth. And that in fact gives us 1. So because these two are not the same, the limit does not exist. So this was in fact simpler than the previous problem. Okay, so let's now do one last example. So this one is another function, and they're asking us to find c so that this function is continuous at the origin. Okay, so because of the denominator of x squared plus y squared, and because they told us find the value, I kind of know that the limit must exist. So I won't go over the details of y equals mx, although for practice you may want to do that. Okay, so we need this. We need the limit of f of xy to be the same as f of 0, 0. So first of all, f of 0, 0 is the one that we get from the bottom, because that's the one that xy is equal to 0, 0, and that is c. So I'll have to find the limit of the top, because that's for the ones that x and y aren't, xy isn't 0, 0. So let's use polar coordinates. So we will use polar coordinates. So why are we using polar coordinates? For two reasons. First, at the bottom here, we have x squared plus y squared. And second, when xy approaches the origin, r approaches 0. So we're going to substitute r cosine r sine in the instead of x and y. So plus 3xy squared over x squared plus y squared is going to be, so that's equal to r squared plus 3r cosine theta r squared sine squared theta divided by r squared. Simplifying this, we get 1 plus 3r cosine of theta sine squared of theta. Now let's see if we can use a squeeze theorem to show that this in fact approaches 0. Well, this approaches 0. This is bounded by 1 and negative 1. So let's see. Cosine of theta sine squared of theta is between 1 and negative 1. Now, I'm going to have to be careful, as we discussed before, we can't multiply both sides of an inequality by negative numbers. So if you are multiplying by something, you have to make sure it is positive. Well, r is always positive. It's the distance to the origin. So we can multiply by r. So we're going to multiply by 3r. Negative 3r is less than or equal to cosine of theta sine squared of theta times 3r less than or equal to 3r. And then add 1, so we get 1 minus 3r is less than or equal to, this is exactly the function that they gave us, x squared plus y squared over x squared plus y squared, and I believe we had 3x y squared. And that's less than or equal to 1 plus 3r. Now, since xy approaches the origin, 1 plus 3r and 1 minus 3r both approach 1. So this one and 1 plus 3r, as r approaches 0, it is 1. So by the squeeze theorem, since both of these two, this one and this one, both approach 1, the middle one also approaches 1. So by the squeeze theorem, limit of f of xy is in fact 1 as xy approaches the origin. So that tells us c must be 1. To summarize, you should be able to draw some of these graphs, quadratic surfaces, and I have gone over a few of them today and in the previous video, but make sure you're comfortable with all of them. There are several of them that I have not gone over them, but they are all in the textbook, so pages 821 and to 823. To evaluate limits of functions as xy approaches the origin, which is most of your examples are going to be xy approaches the origin, find the limit along the lines through the origin, which would be y equals mx and x equals 0. If the limits are not the same, then you know that the limit does not exist. If the limits are the same, you suspect that the limit might exist. So you use the squeeze theorem using inequalities, sometimes using polar coordinates to obtain your final result. And if these limits along different lines are all the same, that does not mean the limit exists. I will see you in the next video.